Can we find siblings of the sun? Is the expansion of the universe symmetrical in all directions? Which molecules can be considered biosignatures? And in Q&A Plus, I answer a tricky question about Star Wars versus Star Trek, all in this question show. It's time for the question show. Your questions, my answers, as always, wherever you are across my channel. If a question pops in your brain, just write it down, I'll gather them up, and I will answer them here. All right, let's get into the questions. Aaron Calhoun, do you think that we will ever find the sun's siblings, the stars born in the same cluster as the sun? Astronomers think that they already have. And the way they did this is sort of two parts, because there's kind of two pieces that you're looking for to try and identify the stars that were born in the same stellar nebula as the sun. The first thing is you're looking for its movement. You're looking for stars that are following roughly the same kind of orbit around the Milky Way that the sun is. Thanks to the Gaia mission, astronomers have been able to map out the movements and positions of about 1 billion stars in the Milky Way. And so they found plenty of candidates of stars that are moving in roughly the same way that the sun is. So that's your first issue. Now there's going to be drift over the course of 4.5 billion years since the sun and its siblings formed, but you're not going to get things that are super weird going in the opposite directions, highly elliptical orbits. You're going to have stars that are kind of moving with the same velocity, same angles, roughly the same kind of orbit. The second thing is the chemical composition. It's assumed that when you have a stellar nebula, the nebula was enriched with roughly the same kinds of metals. And of course, I'm using metals in the astronomer sense, which is anything that is heavier than helium, anything with more protons than helium. And so you're looking for the stellar fingerprint to be very similar. Same amount of carbon, oxygen. This is a process that astronomers can determine by looking at the light of a star. It's called spectroscopy. You essentially take the light of the star, you turn it into this big rainbow, and then you're looking for absorption lines or emission lines in that light that line up to the known absorption lines, emission lines of different chemicals when they are ionized. And you can tell the presence of different kinds of chemicals in the atmosphere of a star just using this technique of spectroscopy. And so there are other surveys that are doing spectroscopy of stars at a vast scale. They are looking at hundreds of thousands, millions of stars, and they are doing this sort of careful, painstaking work of checking the stellar fingerprint of those stars. And so now you cross-reference the two. You are looking for stars that have similar characteristics to the sun, and you're looking for stars that have a similar movement to the sun. And astronomers have found several candidates that they feel fulfill both of those requirements and are good candidates for potential siblings of the sun. And so, we've reported on this in the past in Universe Today. I would say a few candidates have been known over the last about 5 years or so. Mungo Halfbrain. Are we 100% sure that the universe is expanding at exactly the same rate in all directions? We are not 100% sure, but we are pretty sure. And the main assumption that astronomers use is that you are not special, that the place where we exist here in the universe is normal. Now, by normal, of course, we have this really interesting planet Earth, and we have this cool solar system, and we have the Milky Way galaxy and all of that. But at sort of like the largest scales, if you unfocus your eyes and kind of look at the universe, you're going to see roughly the same stuff. That you're going to see galaxies, you're going to see galaxy clusters, you're going to see stars, planets, dark matter, dark energy, and they're going to be in roughly the same kinds of compositions. And once you make that we're not special sort of assumption, then you can make a lot of progress, right? You can say, well, if we count the number of stars that are in the Milky Way galaxy, and then we know how big the Milky Way is, and then we look at another galaxy that we can't count the stars in it, we can estimate the number of stars that are in that galaxy. We can estimate the supernova rate based on the observations that we've done closer to home. And one of these assumptions is that the expansion of the universe is continuing in all directions at roughly the same rate. And that matches the observations. Like, astronomers have done a lot of calculations and observations that reinforce this idea. For example, if you, again, squint your eyes and you sort of randomly pick up chunks of the universe, like large chunks of the universe, and compare them to each other, the variations between those chunks are actually really small, like 1 part in tens of thousands, at the largest scale. Cubic billion light years of material from one part of the universe is kind of exactly the same as one other part of the universe. And so whatever forces are driving the expansion of the universe, the leftover momentum from the Big Bang, the accelerating impact of dark energy, the slowing down of the universe from gravity, from dark matter, and so on, they're roughly the same. And so it's assumed that what we see in all directions is roughly the same. SD Landshire. Regarding the detection of life signatures on the surface of planets, asteroids, comets, what molecule or pattern discovery might split scientists in two? Sugars, lipids? So this is the challenge of astrobiology, really, is what is a biosignature that would be a convincing evidence that there's life on another world? And as you said, the kinds of raw material for life has been found everywhere, both in asteroid samples as well as detected in large star-forming regions. Like, it really looks like before you get a star, the raw materials for life is already present. Amino acids, various hydrocarbons that are used by life, sugars, various gels, gums, all kinds of stuff seems to be present. All the raw materials there and ready to go. Now, we're not entirely sure if there are mechanisms that will deliver that stuff gently to the surface of a planet. If you're delivering a package of amino acids on an asteroid at 20 kilometers per second and you're slamming into a planet, it's not going to hold on to its bonds, right? It's going to turn into a bomb, and then you will have lost all of the amino acids. But so this is still a question. Can you get gentle delivery of the stuff from space down to the surface of the Earth? And I've interviewed people who have sort of explained mechanisms where that might be possible. So it really feels like all of the raw material for life is being delivered to the surface of planets. And then in theory, if there is life and they're going to be going out through its various activities, it's going to have various molecules that are part of it. It's going to have various chemicals that it's going to be leaving as waste products. And that if we could then get our hands literally on those rocks, those waste products, whatever, then we could potentially detect life. And so there's like two sort of versions of this. The one version is like us just trying to find it here in the solar system. We send a rover to the surface of Mars. It finds the most interesting rocks. It collects samples. A future Mars sample return brings those back to Earth, and then scientists look through the rocks to try and figure out, is there a clue that life is operating? It's not just geology, that actually biology participated either now or in the past. And the problem is that if it's in the past, then the actual amino acids, the sugars, all of that kind of stuff, the lipids, it's all gone. All you have are the chemistry that remains, the sort of snapshot. When you think about, say, a fossil, right? Like, a fossil is not a dinosaur bone. A fossil is a dinosaur bone that was replaced by a rock. You don't have the bone. You just have a rock in the shape of the bone. And so it's the same kind of thing, which is that you're going to pick up a rock. It's going to have once had life in it a billion years ago. You're not going to find the life. You're not going to find dead life. You're going to find the chemical results from life. And then that makes it inconclusive again. And so scientists are going to argue. And I think, we've seen the kinds of arguments that scientists have had already about the presence of methane on Mars, the Allen Hills meteorite, the Viking experiment, that those are the kinds of arguments that scientists are going to have and will continue to have, even if we have what appears to be smoking gun evidence of the life. There's no way you could have done this except for life. Some scientists can go, well, I can think of a way that this could have been produced without life. And people are like, yeah, you're probably right. Okay, it's not conclusive. We'll keep looking, right? The only conclusive evidence is going to be actual active life. And that means you're going to need probably liquid water. You're probably going to need a source of energy. You're going to need the kinds of chemistry that's going to be available. Maybe there are places on Mars deep underground where you could find that. Maybe you're going to find that on Europa, Enceladus. This is why those worlds have become so exciting, because water is being vented into space that is enriched by the various chemicals that life needs, that is enriched by hydrogen gas, which life would use as an energy source. All you have to do is take some samples, study it locally, or bring it back home to Earth, and we can get a much better answer. So that's sort of one, which is just this direct observation way. The second method is going to be remote observation. We're going to look at the chemistry and the atmospheres of exoplanets and hope to see the kinds of gases in that atmosphere that tells us that there's life there. And that can be done here in the Earth. You can sample the atmosphere of the Earth. You can measure the presence of oxygen and ozone and methane and water vapor and carbon dioxide and sulfur dioxide and then other hints of other kinds of molecules that are really only produced by life. The problem is that those amounts are very low. And so to make an observation is really tricky. When you think about the observations that were made from Venus, right? They detect the presence of phosphine in the atmosphere of Venus. That's a gas that's produced by life here on Earth. And yet it is inconclusive. Scientists are arguing about whether or not phosphine was actually detected. And even if phosphine was detected, whether it can only be produced by life. We know that there are non-biological ways that life can produce things like phosphine. So this will always be inconclusive until we have boots on the ground, labs on the site. People are doing a lot of work to try and get to the bottom of whether or not this is actually life. Like, yeah, if we saw some kind of Mars rodent scamper past the Perseverance rover, if we saw a tree on the surface of Mars, it would be answered. But we don't see that. And so the amount of what we're going to be able to detect is going to get harder and harder. And then on the other side, of course, some kind of technosignature, some kind of intelligent signal coming from a civilization that has put chlorofluorocarbons into their atmosphere. They recently had a nuclear war, and you're detecting the radiation left over from their war. These are the kinds of things that might be a lot more detectable and give you that certainty. So prepare yourself for decades, if not centuries, of uncertainty. That is what the future holds for the search for life in the universe, which isn't great because, we want an answer to this question, but it is the most profound question that humanity has probably ever asked. And so when we do get the answer, it's going to be sweet. It's time to shout out all the new $5 patrons and above: Hardy, Greg Henderson, Tom S., Tech Dude, Kyle Smith, MP, Brian Altschul, Brian Wilhelmsen, Tenta Mozzarella, and Daniel Griggs. Join the club at patreon.com/universetoday. Juju to full. Since brown dwarfs emit their own glow, is it possible for a habitable zone to occur around them? Yeah, absolutely. Brown dwarfs are considered failed stars because they are not running fusion, like pure hydrogen fusion in their cores. They are too small, too low mass. They do have a form of fusion. They can have deuterium fusion, but it is sort of less energy. They're putting out less heat. You can only really see them in the infrared, but they are putting out heat. And wherever you get heat, that gives you a habitable zone. It's assumed that there are going to be planets around brown dwarfs. They're big, they're massive, they formed. Some of them are going to have planets. And what is probably another contribution of heat is the kind of tidal interactions that we see around a place like Jupiter, that you've got multiple moons, the moons interact with each other and with Jupiter, and that creates this internal tidal flexing in the moons. Io is the most volcanic place in the solar system. Europa probably has liquid water under a thick surface of ice. And so you get this heating. And so you're probably going to get this sort of 1-2 punch. You're going to get the heat coming from the brown dwarf, and you're going to get the tidal interactions between all of the planets that are orbiting around the brown dwarf. And that's going to put things into the habitable zone. But I think it's, you could get liquid water on the surface of those worlds if the conditions are right, but you're not going to get like light coming into that world. So it'll be completely dark. It'll be liquid, but it'll be completely dark. And so you're really limited to the amount of available energy. You're not getting the 1,000 watts per square meter that we experience here on Earth. You're going to get whatever are the chemical interactions that are coming from volcanic activity on that planet. But it's not zero, and so it could theoretically support life. And, we see life that is completely independent from the surface of planet Earth down at the bottom of the oceans. You've got these vents, you've got sulfuric gases that are coming out, and it is supporting an ecosystem in the darkness without sunlight. So if it can work here on Earth, it could probably work on planets around a brown dwarf. Sean Mann, Fraser, what universe would you rather be in, the Star Wars universe or the Star Trek universe? Obviously the Star Trek universe, right? The Star Wars universe is like brutal and cruel and unfeeling, with people always at war, people always gaming for power, with an empire that is exhibiting its brutal authority over a populace, where even people trying to do right are crushed under the thumb of an autocratic empire. No, thank you, Star Trek. Where you've got a grand federation of planets that's trying to do what's best, that they're interacting with a larger universe with curiosity and good intention, where you're in a post-scarcity society where people get to decide what they want to do with their lives because of whatever they find intrinsically exciting. There are threats, there are challenges, but there are bold sort of aspirations that the society holds itself to. I will take Star Trek every day over Star Wars. Yuck. Ugh, I don't want to live in Star Wars. It sounds like a nightmare. It is dystopia. It is not a good universe. It is a bad universe. All right, those are all the questions that we had this week. Thank you, everyone who asked your questions in the YouTube comments, everybody who joined me for the live show. The next live show is going to be on Sunday night, January 4th at 10 p.m. Pacific time. There'll be an event here on the channel. It's a weird time, but it's so that it's Monday afternoon for people in Australia and Japan and China and so on. We're trying to sort of split up the globe and provide a reasonable live stream that people can get at least once a month. And so that's when the next event is. But like I said, there's going to be an event on the channel. You can make sure that you can get notified of when that's going to be, because I know it's at like an unusual time. So I'm going to chat about video games. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Bear Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Bailock, Cy Nelson, Dark Figa, David Gilton, David Matz, Evan Pro, Greg Feely, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Marcel Sitz, Michael Purcell, Nordspace, OneStepForAnimals.org, Paul Roebuck, Renkaidu, Richard Williams, Sean Sargent, Stephen Fowler Munley, Team 49, Telescopes Canada, Wolfgang Klotz, and Zeldaborg Galactic Defender, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. So it's time for the Steam Winter Sale, and the sale ends on January 5th. And so the time you're watching this, there's like another 4 days before the end of the sale. And I'd like to know what you're buying. What games are you playing right now? And which ones should I also play? Especially the ones that are on heavy discount, because I am a deal hound. I've got about 80 games on my wish list right now. And so I just wait for them to come on stupid sales, and then I buy them. And then of course I never play them, but I buy them. And that's halfway to playing them anyway. I'm mostly continuing to be playing Path of Exile 1. The Keepers of the Flame League, I'm playing on Ruthless Solo Self-Found, which is sort of like a more difficult, more torturous version of playing the normal game on the Ruthless mode. It's been a lot of fun. I've learned a ton about the game. Man, Path of Exile is like my perfect game. But I would love to play other stuff when I'm done playing that. Or otherwise, I'm just going to go back to Project Zomboid and RimWorld. So let me know what you are playing. Put them into the comments down below, especially the ones that are on sale. And then I may add a bunch to my own wish list, or even just put them into my shopping cart. All right. I hope you're having a good new year so far. We'll see you next time.